The standard for building AI agents relies entirely on external orchestration frameworks. Developers use tools like LangGraph, CrewAI, and Semantic Kernel to govern models. These frameworks have collectively amassed over 290,000 GitHub stars, becoming the default infrastructure for enterprise AI applications. They all operate on the same premise. An external control system sits above the LLM. This orchestrator acts as a traffic cop, manually passing state variables and injecting routing decisions into the model at every step of a task. A 2026 paper by Simon Dennis and his colleagues argues that this entire architecture is flawed for standard deterministic business workflows. Their research demonstrates that developers can achieve near-frontier agentic quality without the orchestrator, dropping operating costs by 2 orders of magnitude. If an alternative method yields identical performance for 1% of the cost, we have to examine why the industry is still building massive external scaffolding. To understand the inefficiency, look at how an orchestrator actually executes a procedure. When a user makes a request, the framework wraps that input in a massive set of system instructions detailing every rule of the workflow. This creates a strict context window tax. The orchestrator passes the entire procedural instruction set to the LLM, swallowing the prompt space before processing user data. Because the LLM lacks memory, this instructional payload is re-injected every turn. The token count compounds rapidly, and API bills scale directly with it. Handling this repetitive context load requires immense compute power from expensive frontier models. Furthermore, this architecture continuously transmits internal business procedures out to third-party providers. Businesses rely on strict rule sets with zero margin for creative interpretation. Yet, orchestration forces these highly deterministic rules through the probabilistic reasoning engines of generalized models. Using an external system to repeatedly force a generalized frontier model to follow a strict procedure is an inherently wasteful abstraction. The architectural alternative to this waste is what the researchers call a subterranean agent. Instead of holding the rules in an external orchestrator, developers use fine-tuning to compile the procedural workflow directly into the weights of a smaller neural network. By baking the procedure into the model's structural logic, the external routing layer becomes unnecessary and can be removed. This reclaims the entire context window. Because the workflow is now structural, the rules no longer need to be passed as text in the prompt. Prior academic projects, including FireAct and Agent Lumos, have already demonstrated that weight compilation functions as intended, yet developer adoption has stalled. This resistance is driven by 3 distinct perceived barriers within the engineering community regarding the limits of smaller models. To shift industry consensus, Dennis and his team subjected subterranean agents to extreme procedural stress tests to empirically dismantle each of these 3 barriers. The researchers began with 2 distinct empirical test environments, travel booking and Zoom support. Both of these environments are complex, containing 14 distinct procedural nodes each. The first engineering assumption is that small models lack the reasoning capacity to execute strict, step-by-step procedural routing without an orchestrator actively guiding them. In the travel booking test, the subterranean agent accurately navigated the environment, routing users between specific booking nodes and handling constraints entirely on its own. The second assumption is that smaller, fine-tuned models cannot retain intricate, product-specific domain knowledge. The researchers used the Zoom support test to evaluate this. Successfully solving these customer issues required technical knowledge of Zoom's software architecture and troubleshooting steps. The subterranean agent internalized this deep domain knowledge purely through the fine-tuning process, embedding the facts into its weights. Achieving this same accuracy with an external orchestrator normally requires building and querying a retrieval-augmented generation system to fetch the relevant technical documents. The data shows that small, fine-tuned models can autonomously route and retain domain-specific facts without relying on external scaffolding. The final and most persistent engineering objection concerns complex state management. There is a widespread belief that small models will inevitably hallucinate or lose track of their state when placed inside highly branching, multi-turn workflows. To test this assumption, the researchers deployed an exhaustive insurance claims workflow. This chart shows the claims architecture, consisting of 55 distinct nodes. The system must evaluate variables across 6 specific branching junctions. The subterranean agent accurately processed every state transition across these hubs, mapping the erratic pathways using only internal structural logic. It successfully traversed all 55 nodes without a single external state tracking mechanism monitoring its progress. Subterranean agents maintain flawless state continuity, even in massive, heavily branched procedural environments. With the theoretical barriers removed, we can look at the final quantitative performance comparison between the two architectures on the 55-node task. This chart visualizes the baseline. On the left, an expensive frontier model paired with an external orchestrator yields high accuracy, but it suffers from high latency and high operating costs. On the right, the fine-tuned subterranean agent matches the baseline, achieving near-identical accuracy on the exact same task. However, by stripping away the orchestration layer and avoiding the wait times of a frontier API, the subterranean agent drastically reduces latency. The execution cost drops by 2 orders of magnitude, turning dollars into pennies. For procedural workflows, building an external orchestrator offers 0 performance gain, while demanding 100 times the operating cost. This data requires a structural rethinking of how machine learning engineers approach AI applications. Procedural agent development has moved past the reach of prompt engineering. Engineers are finding more success in building automated pipelines to fine-tune specialized models. For deterministic business procedures, abandoning the orchestration trap is the clearest path to building agents that are economically viable, that are strictly secure, and exceptionally fast.